We know that in light microscopy, diffraction is the main resolution limiting factor. We have recapped the basic equation for the diffraction limit, and we have seen that there are several factors that we can adjust to improve the resolution of a light microscopy experiment. First of all, we can increase the refractive index or the opening angle of the beam. And secondly, we can decrease the wavelength. However, the latter option is not always a preferred option, as decreasing the wavelength means we move out of the visible regime of light. UV or X-ray radiation can be very damaging, and also for many practical applications it is highly preferred to work with visible light, albeit for visual inspection. Now we should also realize that one way to circumvent the diffraction limit is by ensuring that the sources are at a distance further spaced than the diffraction limit. In that way we still get a diffraction limited image, but we can clearly identify the different objects as their point spread functions do not overlap. In other words, if we ensure that there's sparsity in the sample, we can still do diffraction limited imaging. This is one of the key factors in super resolution microscopy, as we will see later. Also, we can profit from nonlinear effects, which will also be treated upon by Bernd Rieger in the later lectures. Now, it was already realized in the 1930s that based on the principles of quantum mechanics, we could also find another way to go to higher resolution imaging. And this is an alternative way to decreasing the wavelength by not using photons, but by using electrons. According to the principles of quantum mechanics, each particle also behaves as a wave, and each wave also behaves as a particle. We know that this holds for photons, but it equivalently holds for electrons. It actually also holds for macroscopic objects, but for macroscopic objects the wavelength is so incredibly small that this is a non-practical limit, and also of course there's a lot of mass involved. However, for an electron this is different. It was Louis de Broglie who first formulated the wave-particle duality, so the equivalence between waves and particles. And he actually derived a very simple equation for the wavelength of a particle carrying a specific momentum P. Now we can get a small estimate of the wavelength that would be involved with an electron based on this equation, but we should realize that if electrons travel very fast, so they have a high energy, there should actually be a relativistic correction to this equation. However, let's just get an order of magnitude feeling. So we take the equation of Louis de Broglie, stating that the wavelength is equal to the Planck's constant divided by the momentum of the particle. Now if we insert the rest mass of an electron, which you see depicted here is on the order of 9 times 10 to the minus 31, and we assume an electron accelerated by a potential field of order of 1 kilovolt, so the electron has an energy of 1 kilo electron volt, we can get to a wavelength of 0.03 nanometer. So if we would manage to focus electrons on a sample and collect a signal from that focus beam, we could have a focus as small as 0.03 nanometer based only on the diffraction limit. So this sounds as the perfect solution for our problem. However, making a microscope for electrons turned out to be a very challenging task. So it was already in the 1930s of the previous centuries that people realized that they could get much higher resolution imaging if they would use a microscope that operates with electrons as a focus beam. Now Ernst Ruska was one of the pioneers in this area, and he was actually awarded the Nobel Prize in Physics for his developments around 1986. Also here in Delft there used to be a big research group working on electron microscopy development already from the very early days. This is one of the reasons that Philips started a product line in electron microscopy, which later became FEI and is now Thermo Fisher, who has a very big facility factory in Eindhoven still today.